Alright, so welcome back everyone. I hope you guys are doing absolutely fine and having a fantastic learning experience so far. So we have covered in section 1 and 2 the fundamentals of statistics and probability and distributions. Now in this third video, we'll be covering the last section of this module, that is hypothesis testing. So in this video, we'll first see what is a statistical hypothesis and what is hypothesis testing. Then we'll see what is statistical significance. After that, we'll see type 1 and type 2 errors, and then different types of hypothesis testing, in which we'll see what are the steps involved in hypothesis testing. Then we'll see hypothesis testing for single mean, then for single proportion, then difference of mean, then difference of proportion, then chi-square test and Anova test. So guys, as you can see, there's a lot to cover in this section. So let's start with our first topic now. Statistical hypothesis is an assumption about a population parameter, like population mean, etc. Now to check if the assumption is true or not, we conduct hypothesis testing. So how do we do it? We first define null hypothesis and alternate hypothesis. Null hypothesis is true unless it is proven otherwise, while alternate hypothesis is what we wish to conclude. Let's see a few examples. Suppose a company is selling wine and it claims that each bottle of wine contains at least 300 ml of wine. So the claim that bottle has on an average 300 ml of wine is true unless proven false. So this will be our null hypothesis. Mu is greater than or equal to 300 ml. Now what we wish to conclude to see if our null hypothesis is true or not, the average quantity of wine is less than 300 ml. Mu is less than 300 ml will be our alternate hypothesis. Let's see one more example. Here on an average, the monthly salary of a fresh graduate engineer trainee is considered as 30k INR, which is Indian rupees. Now we want to see if this claim is true or not. So we take a sample of engineers and see if the average salary is 30,000, which is our hypothesis, or it is not equal to 30,000. So here if salary is less or more than 30,000, our null hypothesis will be proved false. This is called two-tailed test because we are testing the equality here. The example of wine bottle is called one-tailed test. In one-tailed test, we test null hypothesis if it is greater than or lower than something. We'll see these tests in detail. But before that, first understand what is statistical significance. Now, statistical significance is a measure to tell if our research findings are meaningful or not. So how do we decide this? We set up a hypothesis and then we choose an alpha level. Alpha level is the error rate with which we are willing to work. It is also called significance level. Usually it is 5%, but it depends on the problem at hand and can be decided accordingly. Now once we have decided our alpha level, then we calculate the test statistic such as T statistic or Z statistic. After that, we calculate p value using the T statistic and compare it with alpha level. Now what is p value? P value is the percentage chance that our results happen randomly. So obviously a smaller p value is desirable for us. That is a smaller chance of our results being random. Or you can say in simple terms, p value is the probability that helps us decide whether the null hypothesis is to be rejected or not. Now if p value is less than alpha, so we reject the null hypothesis. Otherwise, we fail to reject it. So that is how p-value helps us in making the conclusion about our hypothesis. Now if you see the graph, here the shaded area under the curve is the p-value. First curve is showing p-value for a two-tailed test, and second and third curves are showing one-tailed test with left and right tails respectively. Now we have another approach to test our null hypothesis, that is called as critical region approach. In this approach, we find the critical value using alpha and then compare it with the T statistic. Now I'm not going into more details of it. It's a pretty simple method and one can Google it as needed. But p-value approach that we are going to use is a widely used method, so we'll stick with it only. So now let's see what are these one-tailed and two-tailed tests, and how do we use p-values to reject the null hypothesis in these tests. So we'll understand one-tailed and two-tailed tests with the help of this example. It says let's assume mu is the average grade point score of all the students in a state. We have taken a sample of say 15 students and now we are testing our hypothesis. So we will form the following null and alternate hypothesis and use the significance level as 0.05. So we'll first start with the right tail test, which says that our null hypothesis is mu less than or equal to 3 and our alternate hypothesis is mu greater than 3. So after forming the hypothesis, we'll move to the next step. In this step, we'll calculate Z score, but since we are using a small sample size, so we will use the T statistic here. We can calculate T statistic by the formula shown here on the screen. Here X is the score, mu is the average score, S is standard deviation of the sample, and N is the sample size. Now this is only for demonstration purposes, so I'm not going to show the calculation. I'll just assume that we have calculated T statistic by using the above formula, and it is coming out to be 2.5. So it's a simple formula, you just have to plug in the values and you will get the T statistic. So let's proceed with the T value of 2.5. So in the next step, we will find the P value corresponding to T is equal to 2.5. We can use T tables to find P value, just like we did in the previous section in the case of Z score. But that was only for demonstration purpose. In real life, all these things are done by a statistical software or online calculators. So you don't do it manually. Now let's say we got P value is equal to 0.0127 by using an online calculator. So in an online calculator, we have to give T is equal to 2.5 and degree of freedom is equal to n minus 1, which is 15 minus 1 is equal to 14. We'll input these values and we'll get P value is equal to 0.0127. Now in the next step, we'll compare our P value with the alpha level and conclude on a null hypothesis. So here P value is equal to 0.0127, which is less than alpha, that is 0.05. Hence we will reject the null hypothesis that our average mean is less than or equal to 3. So if you see on the right hand side, these things are shown on the curve. That is how we conduct right tail test. Now we'll see the second hypothesis, which says that average mean is greater than or equal to 3. So we'll again find the T value using the formula as shown here. Let's just say that our T value is equal to minus 1.5 this time. Actually the T value would be minus 2.5 as the graph is symmetric, but I am just making up these numbers to show the procedure. So don't go by the numbers, just understand the process. Now we will find the P value using T value that we have calculated along with the degree of freedom, that is 14. We will give this value to any online calculator and we'll get the P value as 0.0779. We can see here that our P value is greater than alpha, hence we fail to reject the null hypothesis. So we can conclude that our average score is greater than or equal to 3. Now all these things are shown on the graph. So P is denoted by the red region and alpha is denoted by the hatched line. Now our red region, which is P, is crossing the alpha, which is denoted by hatched line. This means P is greater than alpha. Finally, we will see a two-tailed test. In this test, we will test if our mean is exactly equal to 3. So our P value for a two-tailed test is always equal to 2 times the P value of either of one-tailed test. So recall we found our P value in the previous case as 0.0127. So for a two-tailed test, it will be multiplied by 2, which will be equal to 0.0254. Now when we will compare this with alpha, we find out that it is less than alpha, and hence we reject the null hypothesis. So that is how a two-tailed hypothesis test is done. But you might be wondering that how do we decide if the test is a two-tailed test or a one-tailed test? Many times in the problem itself, you have terms like greater than or at least, etc. So in such cases, you can easily decide what type of test it is. But many times you don't have this clear-cut information. So you decide it based on the problem. What you do is you choose a one-tailed test if you want to test the hypothesis in a certain direction, and you don't care if you fail to test it in the other direction. For example, you want to see if group A scores higher than group B. So the sole purpose of your study is to check this, and you are completely uninterested in checking the possibility of group A scoring lower than group B. So in such cases, we can straight away use one-tailed test. However, on the other hand, if you developed a drug that you claim is better than an existing drug, and if you opted for one-tailed test in this case, then you failed to test the possibility of the drug being less effective than the existing drug. Now in this case, there could be serious consequences. So if it is not given in the problem, then it is based on the judgment of the researcher. So that is how you decide whether it is a one-tailed test or a two-tailed test. Now again, the p-values and the alpha levels are shown on the graph. P-value is given by the red region and alpha values are given by the hatched lines. Now you can see the red region is not crossing the hatched line, which means our p-value is less than the alpha level. So that is how you conduct two-tailed test. Now guys, there is a good news as well as a bad news. The good news is whatever we have studied so far, it will all be done in R and we will not have to do all these steps manually. But the bad news is that real life scenarios are much more complicated and formation of null and alternate hypothesis requires some serious skills and experience. Now this skill is developed by experience only. It cannot be taught in a class or through a book. But there are certain foundational concepts so that you can apply it in the field and gain experience. But this is a skill that will come with time. So let's move on to the next part. Now there are two types of error that are associated with hypothesis testing. Type 1 error alpha and type 2 error beta. As you can see in the table shown here, we commit type 1 error alpha, which is also known as significance level, when we wrongly reject the null hypothesis, although it is actually true. Similarly, we commit type 2 error, that is beta, when we fail to reject the null hypothesis, when in reality it is actually false. So if the null hypothesis was false, so ideally we should be rejecting the null hypothesis. But since we have not rejected it, hence we have committed type 2 error. So alpha is the probability of committing a type 1 error, which is also known as significance level. Then beta is the probability of committing type 2 error. And finally, power is the probability that null hypothesis is rejected given that it is false, which is given by 1 minus beta. Now the next question is, how can we reduce both type 1 and type 2 errors? Or do we have to do a trade-off between them? If yes, then which one is better or which one will cause less harm? Now in reality, we cannot reduce both the errors simultaneously, because as alpha increases, beta will decrease and vice versa. So we will have to do a trade-off based on the problem at hand. So let's understand this with the help of an example. Suppose in scenario 1, we are doing medical screening of patients for a heart disease, and we are testing our hypothesis as the null hypothesis is there is no disease, and the alternate hypothesis is the person has a disease. So in this case, the type 1 error would be we reject the null hypothesis even though it was true. Hence, we wrongly classified a person having no heart disease as a heart patient. So what are the consequences in this case? Well, he or she may be recommended for further investigation, and later on it will become clear that she has no heart disease. However, if we commit type 2 error in this case, which will mean we fail to reject the null hypothesis when it is false. In other words, we are saying that we classified a person with a heart disease under no disease category. Now this error could be life-threatening. So we can see that in this case, we can afford to commit type 1 error more than type 2 error. So type 1 error is called as false positive and type 2 is called as false negative. We have patient with no disease who is detected with a disease, and he or she may lead to further investigation. And under false negative, a patient having a disease is detected as no disease, which could be a life-threatening situation. Now you can remember this with the analogy of the same example. Suppose you get yourself tested for a heart disease. If you don't have a heart disease, your results would come as negative. But if they come as positive, then it is actually a false positive. It is positive, but it is false at the same time. Similarly, if you have a heart disease, then the result should come as positive. But if they come negative, then it is a false negative. Because results are negative, but at the same time they are false. So I hope this has given some clarity now. Now let's see one more example. There is a murder accused on trial, and a null hypothesis is that he is not guilty, and the alternate hypothesis is that he is guilty. So in this case, if we commit type 1 error, that is, we reject the null hypothesis when it is true, it will mean that an innocent person would be labeled as guilty. And this is a serious injustice. However, on the other hand, type 2 error means if we fail to reject the null hypothesis when it is false, then it means a criminal, a guilty person, is let go by the jury. Now it is also wrong for the society at large, but committing type 1 error in this case is resulting in labeling an innocent person as a murderer. So basically it is all about the trade-off between the type 1 and type 2 error based on the problem at hand, which means the importance of the type 1 and type 2 error will change based on the problem. So that is how you do the trade-off between type 1 and type 2 error. Now that we have developed a good understanding of hypothesis testing, let's dive a little deeper and see different types of testing. So basically there are 4 categories that we will be looking at. First is when n, our sample size, is greater than 30. Then second category is when n, our sample size, is less than 30. Third is when we have a categorical variable. And fourth is Anova testing. So let's see what types of tests we do in each of these categories. Now when the sample size is greater than 30, then we do hypothesis testing for single mean, single proportion, difference of mean, and difference of proportion. Then when the sample size is less than 30, we do testing for single mean and difference of mean. We will be seeing all these tests in the next slides. This is just to give the summary of all the testing. Okay, so next is when we have a categorical variable. In that case, we perform chi-square test. And finally, we have Anova, in which we have one-way Anova, two-way Anova, Manova, and factorial Anova. Now guys, these are so many tests and you might already be feeling overwhelmed. But don't worry, the good news is we will be just skim through these topics so that you know different types of testing. We are not going to solve any problems on this or study them in detail. So don't worry, just buckle up. Within the next few minutes, you will have the basic understanding of all these tests. Now there are total 6 steps involved in a hypothesis testing. These 6 steps are common irrespective of any type of the test. So first we set up a hypothesis. Then in step 2, we decide on the level of significance, that is alpha level. Then the third step is to calculate the test statistic. So this step is different for different types of tests, and we'll see this step for all different types of tests that we have just discussed. Then fourth step is to calculate the p-value using the test statistic. Then in step 5, we make a decision about the null hypothesis. And in step 6, we state an overall conclusion. So these are the steps that are involved in hypothesis testing. Now we are starting with the first test. So as you can see on the screen, at the top I have displayed the steps that are involved in the testing and highlighted step 3 as we will only see this step in detail because rest of the steps are common for all the tests. Then on the right hand side, I will be displaying tests from each of the category that we saw earlier. So first category here is when the sample size is greater than 30. We have 4 tests here: single mean, single proportion, difference of mean, then difference of proportion. So we'll start with our first test, that is for single mean. This test is to check if the hypothesized population mean is equal to sample mean. Or in other words, it is to check if our sample shows enough evidence so that we fail to reject the null hypothesis that makes a claim about the population mean. Now since the sample size is greater than 30, we can use Z statistic shown here. Once we calculate the Z statistic, we can move ahead with the remaining steps shown at the top here. So that is a single mean hypothesis test for sample size greater than 30. Now let's move on to the next test, which is for the single proportion. Recall that a population proportion is a fraction of the population that has a certain characteristic. Similar to testing for mean, here we will check if the hypothesized population proportion is equal to sample proportion. Or in other words, it is to check if our sample shows enough evidence so that we fail to reject the null hypothesis that makes a claim about the population proportion. Again, we will calculate the Z statistic as shown here. So we have P hat, which is sample proportion. Then we have P naught as hypothesized value of population proportion, that which we are testing. And N is the number of trials. So again, after calculating the test statistic, we can move ahead with the next steps as shown at the top. Then our next test is to test the difference of mean. So a difference of mean test is used to compare two populations and to know if the difference is significant or not. Now there are two assumptions associated with it. Assumption number 1, samples are independent. And assumption number 2, that population is normal or n is greater than 30. If n is less than 30, then we follow a different procedure, which we will discuss when we discuss a second category of test. So for now, we are considering the second assumption that population is either normal or n is greater than 30. Now let's take an example of this to understand it better. Let's say a company identified a skill gap among its employees and designed a training program for its 50,000 employees. They ran a pilot and took a sample of 100 employees and then made them go through the module. They took their pre-module score and post-module score and found that the mean has improved. Now we will test this hypothesis that the training program is effective using the difference of mean. So first we will formulate our null and alternate hypothesis using a difference of mean as shown here. The null hypothesis is mu1 minus mu2 is equal to 0. And mu1 minus mu2 is not equal to 0 or greater than or less than 0 is our alternate hypothesis. Then the formula to calculate the Z statistic is given here. So we can calculate the Z statistic and then we can proceed as per the steps given at the top. So that is how we test for the difference of mean. Now the last test in this category is for the difference of proportion. Again, similar to difference of mean test, we use this test to determine whether the difference of mean between two proportions is significant or not. Let's take an example for this as well to understand it better. So a company launches a drug and claims that this is equally good for both men and women against cold. They then took a sample of 200 women and 400 men volunteers and found that 42% women caught cold and 53% men caught cold. Now we will check if we can reject the company's claim. So our null hypothesis would be that difference of proportion is 0. And the alternate hypothesis would be that it is not equal to 0. Then the formula for calculating Z statistic is shown here. Now this is a complicated formula, so you don't have to remember this formula at all. In fact, you don't have to remember most of the steps that we are discussing here. It will all be done in the software, but you must know what is happening in the background and have some idea of the concepts. That is the whole purpose of explaining these steps. So again, we will calculate the Z statistics from this formula and then we can proceed with the steps shown at the top. So that is how we test for the difference of proportions. Now let's move on to the next category of testing, that is when sample size is less than 30. So in this category, our first test is for single mean. Now here the only difference from our previous single mean test is that the sample size is less than 30. Now since the sample size is less than 30, so here we will use T statistic instead of Z. So the formula for T statistic is shown here on the screen. Now notice in the formula we have divided the standard deviation by the square root of sample size n for calculating the T statistic. So again we'll calculate the T statistic from this formula and then we'll proceed with the rest of the steps as shown here at the top of the screen. Now let's move on to the next step in this category, that is for the difference of mean. So we have already seen this when the sample size was greater than 30. Now the only difference is that in this case the sample size is less than 30. So when the sample size is less than 30, in this difference of mean test there are two possibilities. One is that our samples are independent, and the second possibility is that the samples are dependent. Now dependent samples are also called as paired data. So let's see what are independent and dependent samples. Now independent samples are samples selected from one population that has no relation with the sample selected from the other. Or you can say that each subject has one observation. And then in the dependent sample, each measurement in one sample is matched or paired with a particular measurement in the second sample. Or we can say that each subject has two observations. So this is the basic definition of independent and dependent samples. Let's see one example of each to understand this better. First we'll see an example of independent samples. So let's say we have got two brands of petrol or gasoline, say brand A and brand B, and we want to compare the mileage given by these two brands. So what we did is we randomly chose 5 cars and assigned them brand A and chose another 5 cars and assigned them brand B. Now this type of sampling is called independent sampling because observations from group A and group B have no relation, or you can say each subject, that is each car, has only one observation. Then we took these two brands and this time we assigned both the brands to the same group of 5 cars. So first we asked them to use brand A and then use brand B. Now this is an example of dependent sample. Here you can see that each subject, that is each car, has got two observations, which is mileage from using brand A and then brand B. So this is the difference between independent and dependent samples or paired data. Now the independent sample test can further be divided into two cases, that is pooled variance and unpooled variance. And as far as the dependent sample test is concerned, there is only one case, that is paired sample t-test. So let's see each of these one by one now. First is the pooled variance. So we have two assumptions here. First assumption is that variance of population 1 is equal to variance of population 2. That is why it is called pooled variance. And second assumption is that population is normal. So here we use common standard deviation denoted by SP by using the pooled data from both the samples. Now the formula for calculating the common standard deviation SP is given here. We can also use thumb rule, that is standard deviation of sample 1 divided by standard deviation of sample 2 is between 0.5 to 2. After calculating the common standard deviation SP, we can use the T statistic formula as shown here and calculate our T statistic. And then we can use the degree of freedom as given here n1 plus n2 minus 2 for calculating the p-value. And then we can proceed with the rest of the steps as shown at the top. So that is how we carry out the difference of mean test in case of pooled variance. Then we have the next case as unpooled variance. So when the assumption of equal variances is not valid, we need to use separate or unpooled variances. However, the second assumption of normal population is still true. Now the formula for calculating the T statistic is shown here. Here S1 and S2 are standard deviation of each of the samples, and N1 and N2 are the sample size. Then the formula for degree of freedom is shown here. So to calculate the degree of freedom, we are using a variable C, which can be calculated by the formula shown here at the bottom of the screen. Again, as I said earlier, you don't have to remember all these formulas. Just have a look at it and move on. So after calculating T statistic, we can proceed with the rest of the steps as shown here at the top of the screen. So that is how we carry out the difference of mean test when the sample size is less than 30. Now let's see the difference of mean test in case of dependent samples. So in case of dependent samples, we have paired t-test. We know that each subject is measured twice, resulting in pairs. Also, our assumption about the population being normal remains valid for this test as well. Now the formula for calculating t-statistic is given here. Here d bar denotes the sample mean of the different sets. We can calculate d bar using the formula as shown here on the screen, and then we can use d bar to calculate t value. So that is how we do the difference of mean hypothesis testing when sample size is less than 30. Now let's move on to our third category, that is chi-square test. So chi-square test is applied when we have two categorical variables for a single population. For example, in an election survey, voters can be classified as per the gender, and then they can further be classified based on their voting preferences. So in this case, we can use chi-square test for testing if gender and voting preferences are independent of each other or not. So let's see what are the steps involved in chi-square testing. The first step is to create a contingency table of the observed data. Now the table shown here is called contingency table. Contingency table displays the relationship between several categorical variables. We can see here we have information such as how many men and women have voted, how many votes have been given to candidate A and candidate B, etc. So this is called as contingency table. Then the next step is to find the expected count. So expected count is given as row total multiplied by column total and divided by total sample size. Now once we have calculated the expected count, we will create a new table using the expected count. After that, we will use the chi-square statistic x square. We will use this statistic to check if the observed data differs from the expected count. The formula for chi-square statistic is shown here. Here Oij is the observed value of two categorical variables and Eij is the expected value of two categorical variables. Now again I am restating, you don't have to worry and remember these formulas. The only important thing is that you understand the concept behind it. All these calculations will be done by our software, so you don't have to worry about the formulas. Now there is a small note given here. It says, in general, if 20% of expected count is less than 5, then chi-square test is to be avoided. So that is how you perform chi-square testing. Now let's move on to the last category, that is Anova testing. So Anova test stands for analysis of variance test. Just like the t-test that we saw earlier, Anova test can also compare means. But the advantage with Anova test is that it can compare means of more than two groups. Now we could also use t-test for multiple groups, but that is not a feasible choice. And it also increases the chance of error, as every time we do a t-test, we will commit some amount of type 1 error. And it will add up if we repeat that process for multiple groups. So that is the reason it is preferred to use Anova test. Now let's see where we can use Anova testing. Suppose you have a group of athletes and we have divided them into three groups: amateur, mid-level and professionals. Now we want to measure their strength levels. So in this case we can use Anova testing. The strength level is our dependent variable and our independent variable is the type of athlete. So as you can see here, we have three groups: amateur, mid-level and professional level. So instead of using t-test for multiple groups, it's better to use Anova here. So in Anova test, we will have to calculate the F statistic instead of the T statistic. And we will always do it using the software. Then after calculating the F statistic, rest of the steps remain the same as shown here on the top of the screen. Now here in the table, I have shown the steps that are required to calculate the F statistic. Obviously, you don't have to remember this because all of this will be done by the software, but just have a look at it and then we'll move on. So first we calculate the sum of squares. Now there are two types of sum of squares, between the group and within the group. Formula for both the sum of squares shown here. Then in the next step, we'll calculate the degree of freedom. Again, the formula for degree of freedom is shown here. Then using the degree of freedom, we will calculate mean squared variance between the groups and within the groups. And then finally, we'll calculate the F statistic, which is the ratio of between the group mean squared variance and the within the group mean squared variance. So that is how we carry out the one-way Anova test. Then we have two-way Anova test. This is nothing but an extension of one-way Anova test. We use a two-way Anova test when we have one dependent variable and two independent variables. Let's see an example where this test can be used. We will again refer to our earlier example of athletes. So we had a group of athletes and they were divided into three groups: amateur, mid-level and professionals. Now this time we also have their dietary habits. Let's say vegetarian or non-vegetarian. So now based on these inputs, we want to measure their strength levels. So here we can use two-way Anova test. The strength level is our dependent variable and we have two independent variables, that is type of athlete and their dietary habits. Again, the procedure remains the same. We will calculate the F statistic using a software package and then follow the remaining steps which are shown here at the top of the screen. So that is how you conduct two-way Anova testing. Then the last test is Manova. Now Manova is just like an Anova test, but it has several dependent variables. So we will go back to our athlete example again. Here we have three levels of athletes and their dietary habits. But this time we want to compare two dependent variables instead of one. So we will measure strength level as well as their annual income. So in such cases, when we have more than one dependent variables, we can use Manova test. Again, the procedure remains the same. We will first calculate the F statistic and then follow the rest of the steps. So that is how you conduct Manova test. Now there are other hypothesis tests as well, but they are beyond the scope of this module and are not required at this point. So with this, we have completed the last section, hypothesis testing of our first module, basic statistic. Now let's quickly revise what we have covered so far. So in this video, we have learned about the statistical hypothesis and its testing. Then we discussed about statistical significance and how it is used in conjunction to p-values to arrive at a conclusion. We also saw one-tailed and two-tailed hypothesis testing with examples. We also had discussed about type 1 and type 2 errors. And finally, we saw different types of hypothesis testing, where we saw what are the steps involved in a complete procedure of hypothesis testing. Then we discussed about different types of hypothesis test. Here we only discussed the procedure to calculate the statistic, because the rest of the steps are same for all the hypothesis tests. So in the different types of hypothesis testing, we discussed about single mean, single proportion, difference of mean, difference of proportions. We also saw different cases where we have dependent and independent samples. We discussed about chi-square test, one-way Anova, two-way Anova, and Manova. Now with this, we have completed this module, basic statistics. So I know guys, it was filled with a lot of terminologies and theoretical concepts. But remember guys, this is required to build a solid foundation for our data science career. Believe me, there is no data science without these fundamental concepts. And you will see this as we move along in this course. Now many of the concepts that we have studied will be applied directly, while some will be useful at a later stage. And I'm sure you must have seen the way I tried to explain all these concepts in the simplest manner. Because as I said earlier, I had studied these things and they always have confused me. So I wanted to present it in a way that anybody who doesn't even have basic understanding of statistics can also understand it. So I hope you enjoyed the videos and found them helpful. If you like the videos, do give it a thumbs up, subscribe to the channel and share it with your friends. Now I'll see you guys in the next module, that is R programming. So until next time, keep learning and have a great day.